demonstration for the bridge?
Excuse me?
Demonstration?
Yeah, I can do that. Thank you.
So this the one have to sign it too?
Yes. She has a separate grade for her class. Do what? Okay, here you go. Alright. So, unfortunately, I have to start off this lecture with some bad news. I'm not sure how many people noticed, but when I sent out the quiz on Friday, I sent the wrong version. And the version of the quiz I sent out had the answers at the bottom. So, I can't in good faith take that as a quiz grade, but I don't want to, you know, just disregard all that work. So I'm going to count it as an extra credit grade. Okay? So, thank you for turning those in. If you turned it in, you're going to get extra credit. Now, the quiz, I still do want to know how y'all are doing with this content, so I am going to basically give that quiz again, but it'll be in a different order of questions, different values for the questions, and there will be other stuff added to it, like what we're going over today, standard deviation. Okay, so Friday we're going to have another quiz to supplement our grade. Okay, so let's go ahead and take roll.
You on Zoom?
I'm on YouTube right now. Osa, you're here. Johnny's not here. DeAndre is here. Aliana is here. Milo James is here. It's not here. Yeah. I think he's been joining through YouTube lately. Yeah. Sarah is here. And that should be everybody. Okay. So, what we have been going over lately is measures of location. And what we said last time we were talking about this was that we can use some very basic, simple measurements, mean, median, and mode. However, mean, median, and mode, they tend to change based on what our data is doing, and they're only a single point in our overall data. You know, we want to describe what our data is typically doing, but if we just have a single point, I mean, not all of our data is going to fit that exact point. Okay? So there's another measurement that we can use to find where all of our data is basically located, and that is standard deviation. Standard deviation is a measurement of how much our data varies from one point to the next. And if we think about it on our normal distribution, so one of these curves like this, again, our mean would be right here. Our mean, median, and mode would be right there in the center. Now, what we can do with the standard deviation is we can find a number to see how varied this data is and add that number to this side of our mean to find an upper boundary and subtract it from this side to find a lower boundary. Okay? So -1 standard deviation from the mean to find this boundary, +1 standard deviation from the mean to find this boundary. And again, what this does for us is now this range is where most of our data is going to fall, between these 2 points. And so instead of just having a single value for what our data should look like, we now have a range of what those data points should look like. So anywhere from here to here, that data is going to fall into there. And it'll be a certain percent of our data that falls inside of this range. Okay? Anything outside of this range is an outlier, kind of like a wild card, you might say. You know, if we were to take the heights of all the people in the world, okay? Some people are very, very short, some people are very, very tall, but most people are somewhere between 5 and 6 feet, or 5 and some odd 6 feet. Okay? So you might have some people that are at 2 or 3 feet, and some people who are at like 7 or 8 feet. And they're the outliers, but most people are going to fall into the range here between these standard deviations. Does that make sense? Mm-hmm. So this allows us to see where most of our data falls. Now, before we get into the actual calculations, let's go over some symbols, because these formulas use a lot of symbols. Some of them we've already seen, like n. N is the number of data points in our set. So like when we calculate our mean, we add up all the numbers and then divide by the number of numbers in our set. That's n. We're dividing by n. So n is the number of data points in a set. Okay. We also have x. When we have a set of data, any point in that set is x. So when we look at tables of data, they're usually labeled, and they'll be labeled, x and y, something like that. X is just the data. So like if we took the height of everybody in this class, each of your heights would be an x value. Okay? So x is any data point. Okay? And another one that we've gone over before is capital sigma. It's one of those Greek letters. What capital sigma means is that we are going to take a set of numbers and add them all together. Sigma just means sum, and of course sum means you add. So it's a sum of a set of numbers. Okay. Now at this point we need to make distinctions. Remember that there are two ways that we can collect data. We can either collect them as a population or as a sample. So what is a population? What does that mean about our data? It's everything in a particular group. So the height of all NBA players would be a population. The number of pets each person owns in a neighborhood is the population. Okay? So what is a sample? A portion, yeah. Good. So sometimes we can't get a population. We have to go for a sample because it's either, more cost effective or more time worthy, or it's just not possible to get an entire population for what you want to do. For instance, if we wanted to survey every single person in the world, it's not really possible. You'll have to take a survey of certain groups. And so that'd be a sample. So a population is the entire group. A sample is we're taking some in that group and trying to see what they look like and project it to the rest of the population. So, in order to help keep our minds straight about which one we're talking about, population or sample, we have different symbols. So, for instance, mean. In a population, mean has the symbol mu. That's Greek mu. And the standard deviation for a population is sigma, lowercase sigma. So lowercase sigma is like a circle with a tail on top of it. Okay, so in contrast to mu and sigma, when we're talking about a sample, the mean is going to get the symbol x bar. So it's the same as the mean of a population, but to understand which one it's calculated from, a population or a sample, we call a population mean mu and a sample mean x bar. Again, this is to help us understand, are we talking about a population or are we talking about a sample? Because we handle these two types of data differently. Standard deviation gets the symbol S. So in a population, standard deviation is sigma. In a sample, standard deviation is just S. Okay. Now again, populations and samples are handled differently, and the calculations are sometimes, at least, different for them as well. Mean for a population, like we know, is you take all the numbers in your data set, add them together, then divide by the number of data points you have. So this would be mu equals, so sigma, sum of all numbers in a set, and then we have to say what set we're talking about, where we're adding up all the x points, all of our data points. And then we divide by the number of data points we have, so that's n. Okay? X bar is actually the same. X bar is also the sum of all data points, so add up all your data points, divided by n, or divided by the number of data points you have. Again, this is just mean. We know how to calculate mean. And it's not different between a population and a sample when you're calculating mean. What is different is our calculation for standard deviation. So for a population, standard deviation, or sigma, lowercase sigma, is the square root of sigma, or the sum, of x minus mu squared all over n. Okay? So this is very, very similar to our mean. Basically, this is doing that mean a second time and adding a little extra there. The standard deviation for a sample, again, it's similar, but a little bit different. So standard deviation for a sample, S, is sigma x minus x bar. So remember, mu and x bar are basically the same idea. They're both mean. Squared all over n minus 1. So there's the difference, is that in standard deviation for a population, we're going to be dividing by n. For standard deviation for a sample, we're going to be dividing by n minus 1. So think about it this way. In a population, we know all of the data points in that group. We took the entire group, we got all the data points for it, and we have them represented. We have the entire n. For a sample, we're trying to take a few data points from a group and then project them onto the rest of the group. So whatever goes for this smaller section that we pulled should be true for the rest of it as well. But to account for the fact that we don't have the entire group, we use n minus 1. And there's some mathematical reasons for that, but that's the big distinction. Does this make sense? Any questions? None? Okay. So again, we have to keep in mind that we have to treat populations and samples differently. Let's go ahead and practice this. Okay. So let's try a population first. So remember, a population, the mean is sigma x over n, which is the first thing we want to know, because in standard deviation, we need to know that mean. So the standard deviation for a population is sigma equals the square root of the sum of x minus mu squared over n. So let's get some data in here. Let's say we're running some statistics for a dog pound. And they have 5 dogs currently. Okay? So we want to know the height of each of these dogs and find the best fit for the biggest group. So maybe we're building kennels or something like that. We need to know the height of each dog. And we need to know, standard, what is a dog's height. So what could we predict a typical dog's height is going to be? So we want to know the mean and the standard deviation for that. So we measure the dogs. They have this kennel or pound or whatever. And in millimeters, from the bottom of their paw to the top of their shoulder is 600 millimeters. Then another one is 470 millimeters. Then we got a short one at 170, 430, and 300. So each of these is a dog's height. And again, what we want to know is we want to know the mean and the standard deviation so that we can understand what a typical dog's height is. So typical dog in this group. Okay? So first, let's calculate that mean. So we need to know in mean the sigma x, or sum of all x points, and the n. So let's start with the sum of all x points. So we add up all of our points. So 600, 470, 170, so on and so forth. We add all those up. We're going to get 1,970. What is our n? 5, because that's how many data points we have. Good. So n is 5. So our sigma x over n would be 1,970 divided by 5. Let's see, that would come out to 394. So there's our mean, mu. So our mean is 394 millimeters. So on average, a dog's height is going to be somewhere around 394. But again, to know typically where that height's going to be, we need to find the standard deviation, because it's going to be somewhere around here, but we need to know where exactly around this number it's going to be. So now let's go into our standard deviation. We've got our mean, so that's good. We've got all of the pieces and parts we need for this. We need to use our order of operations to work through it though. So first step in order of operations is parentheses. We need to do what's inside the parentheses first. And inside the parentheses says x minus mu. So what that means is we're going to take each of these x points, each of these x values, and subtract mu from it. Subtract our mean from it. Okay? So 600 minus 394, that's going to give us 206. 470 minus 394 is going to give us 76. 170 minus 394 is negative 224. 430 minus 394 is positive 36. And then 300 minus 394 is negative 94. So there's our part in parentheses done. Next, after parentheses comes exponents. So we have a square here, so that means we need to square all of these numbers. So x minus mu squared. Square all these numbers. Don't worry, I won't make you square them. 42,436. 76 squared is 5,776. Negative 224 squared is 50,176 positive, because remember, a negative times a negative is a positive. 36 squared is 1,296. And then negative 94 squared is 8,836. Okay, so again, we get the x minus mu, then square it, and then the only thing left up here to do is get that sum. So we need to add all of these data points together. Basically, we're getting another mean. It's just instead of taking the mean of this data set, we're taking the mean of this squared data set. So add it all up. Sigma x minus mu squared is going to be 108,520. So there's us adding up all our data points, and then divide by n. So sigma x minus mu squared over n. So again, our n is 5. So divide 108,520 by 5, and we get 21,704. Now we just have one more step to get our standard deviation, and that is to, let's see, we've done all that in here. We've divided by n. Now we need to take that square root. So if we take the square root of that, it does not come out to what we call a rational number. It has a decimal that keeps on going on and 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 never repeating, never having a pattern to it. It's irrational. And so we have to round it. So the number that we get when we take the square root of 21,704 is 147.32, which, since we're talking about millimeters, we will just round that to the nearest whole millimeter, so 147. Okay, so the standard deviation between these dogs' heights is 147 millimeters. Again, what this means is if we think about this on a normal distribution, our mean, which is 394, is right here in the center. Now, to find the range, or the space that most of these dogs fall into for their height, we first say, all right, below this is one standard deviation. The way we figure out where that is take the mean and subtract the standard deviation. So 394 minus 147 is 247. And then on the other side, we want to go another standard deviation. So instead of subtracting, we will add it. So 394 plus 147 is 541. So for this group of dogs here, the mean is 394 millimeters, but that doesn't really fit the dogs well. It's just a single point. It's better to say that most of these dogs fall between 247 millimeters and 541 millimeters. If we look at our data, we have a dog that falls outside of there, 170, that's down here, but it's only one of them. And that's why we see this tail here. Remember that the height of this curve shows us how many data points we have for this value. So like 394 has the most data points available for that. 170, hardly anything there, maybe one data point. We have another one, 600, that's really tall for a dog. It's over here outside. 170 and 600 are both what we would call outliers. They lie outside of the normal standard distributions. Or standard deviations, I'm sorry. So most of our data, in fact, let's see, 1, 2, 3 out of our 5 points fall in this range here. So this is a good way of describing what most of our dogs look like. So we know that if we build kennels for this place, they need to be in this range. Most of them need to be in this range. But we have some dogs that, they're tiny. They'll still probably fit in it. But some dogs are really big, and they're not going to fit in those kennels if we build them for a range like this. So this helps us understand, okay, most of them need to be like this. We need a few that are a little bit bigger, though. Any questions? Excuse me? Without all those steps? Use a calculator. So I did talk to Miss Lamar, and she wants you to first learn how to calculate these by hand. Okay, and so if you wanted to find standard deviation by hand, this is how you do it. Again, it's really like you're finding the mean and then finding the mean again. It's just between finding it again, you have to subtract the mean from all your x values and square those x values. And then you can find your mean again. Basically, that's how it's working. Again, I'll show it to you on the calculator, but Ms. Lamar wants you to learn how to calculate it by hand before you start using the calculator. She wants you to understand why these formulas work the way they do. So if I go to my calculator here and hit stats, I can edit my lists. So put in all the data that I want in here, and I'll go ahead and do that real quick. Let's see. Edit. Clear. All right. So we've got 600, 470, 170, 430, 300. We're going to need to put those into our list for X. So 600, 470, 170, 430, and 300. And so there's all of our data for X values. So we quit out of there and go back to stats. Instead of going to edit to find our list, we go to calc and then hit 1var stats, calculate it. I just need to make sure this is set back to the normal. Calculate. So we have our X bar or mu, whichever one, and sigma and sigma x, all of these in here. And somewhere in here is our standard deviation. I can't see it though. Maybe it's calculating a sample instead of a population. But yeah, your standard deviation can be calculated with these calculator programs, basically. But once again, Miss Lamar wants me to teach you how to do it by hand before we ever go to learning how to use a calculator. Any other questions? Okay. So, real quick, let's look at a sample standard deviation. So this one, I got this one from online, and it says, let's see, a sample of 4 students was taken to see how many pencils they were carrying. Okay, so this is a sample because it's just a selection of the people in a group. So our mean is called X bar, and it is, again, the sum of all the data points in our set divided by the number of data points in our set. The standard deviation is called S, and it is the square root of the sum of all data points minus X bar squared all over n minus 1. So when we polled these 4 students, they told us they had 2 pencils, 5 pencils, and 7 pencils. Now when I have you calculate the standard deviation, it's probably going to be more numbers like this, small numbers. Okay, so first we need to find the mean. Again, mean, we've done it many times before. Add those numbers up, divide by how many numbers we have. So 2 plus 2 plus 5 plus 7. Our sum is 16. So add all these up, we get 16. What is our n? How many data points do we have? 4. So our mean is the sum of all x divided by n. So what is 16 divided by 4? 4. Good. Okay. So now that we've got our mean, X bar, yeah. So now we've got our x bar, 4. We can find our standard deviation. So remember, what we have to do first is x minus x bar, or x minus the mean. So we take each of these data points and subtract our mean. So 2 minus 4 is what? -2, thank you. Same thing here. 5 minus 4? 1. 7 minus 4? 3. And then we need to square those. So x minus x bar squared. So square each of these numbers. -2 squared is what? +4, actually. So a negative times a negative is a positive. So when we square a negative number, it's negative times negative. So it's 4. 1 squared is what? 1. And 3 squared? 9. Good? Now we need to sum all of those numbers together. So 4 plus 4 plus 1 plus 9. Let's see, 4 plus 4 is 8, plus 1, yes, good, 18. Excellent. Okay, now we need to divide this whole thing by n minus 1. So what is our n minus 1? What are we dividing 18 by? Well, what's our n? 4 minus 1 is 3. So 18 divided by 3 gives us what? 6. And then one last step. We got all that stuff there. We now need to do the square root. So the sum of all those values squared over n minus 1. Find the square root of 6. Square root of 6 is going to give us about 2.45. Since we're talking about pencils, though, and we don't really have, half a pencil. I mean, you can, but it still counts as a pencil. I'm going to call this 2. So I'm going to call our standard deviation here. Oh, sorry. So I'm going to call our standard deviation here 2. So if we were to put this on a normal distribution, our mean we said was 4. So our standard deviation being 2, if we take 2 steps this way, we get 2. If we take 2 steps this way, we get 6. So the typical student is going to have 2 to 6 pencils with a mean, an average of 4. Any questions? Yes, sir.
I think you get to 2.35.
So we did all this, got down to 6, and then all we needed to do left was take the square root. So 6, square root of 6 is 2.45. And it keeps on going. There's more decimals after this, but rounded. Does that make sense? Okay. Any other questions? All right, cool. So I think that'll do it for today. Remember that Friday we're going to have another quiz. Other than that, I will see y'all on Wednesday. I hope you have a good day.